Hello everyone, and welcome back to the next video in this tire mini-series. In the previous video, we identified the most common tire forces and heat flows. Now, in this video about testing and modeling, we will begin to explore how these can come together into a more usable package for us engineers. So, why do we test? It's typically a good engineering practice to test our designs and ensure that they behave as we would expect them to given a certain type of stimulation. Moreover, proper testing yields us the necessary data to validate our decisions. In the case of tire testing, we use this information to begin developing our tire model, which is the most fundamental element of a car model. Now, spoiler alert, Hooke's law doesn't work well for tires outside of low speed, lane change maneuvering. In fact, the stiffness is highly dependent on many factors, but in general decreases rapidly with increased steer angle. Thermal and wear testing can help us predict how the car's behavior can change with each lap. If we can get all of this right, we can use this in a simulator and get really close to an optimal vehicle setup or design. So let's see how this type of testing is conducted. The first type of testing we'll discuss is the most popular type, belt testing. I got this picture from CalSpan, who, if you're going to be working with tires, you should get familiar with. The belt tester mounts a wheel and tire onto a movable hub with load sensors and actuators, which measure the force outputs and constrain the motion of the tire simultaneously. The road surface is mimicked by a rough grip belt, which is spun on a rotating drum to give the tire speed. This type of testing is pretty standard. However, there have been discrepancies that say the data may be off by around 15% due to roughness differences between the belt and the actual road. So if the belts are inaccurate, why not test on the actual road? Well, that's the main advantage of the trailer testing. There's several papers about people who have even DIY built these themselves. What we're looking at is a similar device to the belt tester, but now instead of a drum with a belt, we are physically towing this entire device behind a truck and putting the tire on the actual ground. There's even versions of these with water cannons that can measure how much water the tread pattern displaces. A potential disadvantage with these is getting those really big steer angles without upsetting the stability of the trailer and causing a hazard. Additionally, controllability and repeatability begin to degrade as road surfaces vary in roughness and temperatures. Finally, wheel force transducers can be mounted directly onto an existing car. Now, we can test tires with the actual car and road they're going to drive on. While this does pose repeatability and controllability issues, it can be very beneficial if one wants to see how car setup changes can affect the tire. I've heard rumors that this is an extremely expensive testing method, but I wouldn't know exact pricing schedules. In the end, the testing method I recommend is however much you can afford, because if you have real tire data, you are already leagues ahead of several professional motorsport teams. A typical result will look like this. I call it a curve of diminishing returns. As we can see in the highlighted region between -1.5 to 1.5 degrees of slip angle, the slope of the curve is steep and constant. This is what we call our cornering stiffness. Outside of the highlighted region, though, we can see that increasing steer may not necessarily mean an increase in tire force. For this curve in particular, if we're at 6 degrees of slip and want to increase to 8 degrees, we'll actually generate less force. So what can we do to increase the force then at these big steer angles? I encourage you to pause here and think about this for a moment. Assuming you're back, because tires are mostly just friction forces, we can actually increase the normal load on them. This plot from Farhat et al. Shows us different superimposed tests with varying normal load. As we can see, higher normal load yields a bigger cornering stiffness with a little bit of a further slip angle peak. Furthermore, tread temperatures have an effect as well. In this case, the optimal temperature is the one which creates a curve with the largest area underneath it. Now is a good time to discuss the concept of a friction circle. The plots we just saw were all about lateral force, but what about longitudinal? What about combined? The reality is that the longitudinal curves look similar to the lateral ones, but there's a coupling effect between the two that must be discussed. A tire cannot be at peak performance in both lateral and longitudinal directions at the same time. Rather, it can only make a resultant vector of a certain length, which we will call F max. For peak performance through a corner, we need to ride the edge of our friction circle at all times. Let's look at the example of a right-hand turn on the screen which chronologically goes from red to blue. At the beginning of the sequence, red, the car is braking in a straight line, getting the best stopping performance because there is no steering input. At orange, we are braking and turning. At yellow, we are in pure cornering. Here, there is no input from the brakes or throttle pedal, so we are getting the maximum lateral acceleration. At green, the throttle pedal is applied and the steering wheel is partially straightened out. Finally, at blue, the car is pointed straight out of the exit of the corner and is in pure longitudinal acceleration. I once again encourage you to pause the video and work through the 5 stages of the corner again, and think about what the slip angles and slip ratios are for each stage. Are they positive, negative, zero, large, or small? Understanding this is crucial for the next lessons on cornering. Now, I recognize that many people viewing this may be part of an FSAE team, and I've got good news for you. There is something called the FSAE Tire Test Consortium, which is a bank of tire data for Formula Student. The team at Calspan tests all of the Formula tires on their belt tester and gives access to the data for $500. As someone who has worked in the industry, I can tell you that $500 is the cheapest you will ever come across data like this. For reference, one set of GT3 tires costs about $2,500, and proper testing requires something about 6 sets. So to get this kind of data for cheap is truly a blessing. Doctor's orders, this should be the very first thing that any FSAE team should invest in. Now that we have the tire data, we need to package it into a model that we can use to study performance mathematically. This can be an equation, a Simulink block, or a function. What matters is the ability for your program to be able to identify what force your tire is outputting based on its deformation. The gold standard of this process is the Pacejka magic formula. This is essentially a type of regression curve, and it is important to know that we call this an empirical tire model. By calling it empirical, we mean that the coefficients in equation 6 have no physical meaning. Rather, they just change the shape of the tire force curve. There's different versions of the magic formula, and for any modern engineering, it is recommended to utilize version 5.2 or later. The presented version that you see, equation 6, is the original version. The newer ones are quite large and can take up the whole page. For more info on this, take a look at Pacejka's book, Tire and Vehicle Dynamics, 3rd edition. My personal favorite tire model is called the brush model. It's a type of physical tire model where you can imagine the tread of the tire as a collection of brush elements scuffing across the ground. As these bristles enter the contact region, they are deflected, thereby producing tire forces and moments. These deflections only occur within the contact patch. A big advantage of this model is the separation of the contact patch into a sliding region and an adhesion region. This makes it easy to include provisions for tire wear and thermodynamics by saying wear and heat is generated in the sliding region. Based on the size of the sliding region, we can calculate how much the tire is degrading and how much heat is being generated at an instant in time. Much like Pacejka's formula, there's also different versions of this model. A decently advanced version is called Tame Tire and was developed by Michelin. Finally, we have F-Tire. This is a finite element method where we break the tire down into several tiny elements and apply stiffness characteristics to each element in the mesh. This is the most advanced way of modeling your tire, but is computationally demanding and not recommended for student teams. In the next video, we'll talk about some of the work that needs to be done to prep your tires before and after an event on track. Additionally, I'll introduce common modes of failure to keep an eye on. If you're a motorsport tire tech, I highly recommend watching this next one. Thank you.